Okay, so the reason why looking at flow and flow rate is important is because when we talk about stroke volume and cardiac output, remember what stroke volume is. It is the volume of blood that the heart pump out per beat, or the volume of blood that pump out from either the left ventricle or the right ventricle per beat. And the cardiac output is the stroke volume times the heart rate, because the definition for cardiac output is the volume of blood that the heart pump out per minute, and the heart rate is the number of heartbeats per minute. So if you multiply stroke volume by the heart rate, you get cardiac output. Um, so using the hydraulic orifice formula, you can calculate the flow rate. That is the volume traveling for a certain time. So it's going to travel, that volume is going to travel for a certain distance. Okay? But the flow rate is the definition is the cross-sectional area times the flow velocity. Um, we draw, we, you know, in trying to explain this, we drew, you know, a container. So if you have a glass, okay, this glass is just not gonna cut it. All right, so let me draw a glass down here. So if you have a glass and you fill it with, say, water, so if you have a glass and you fill it with water, okay, you can calculate the volume that's in the volume of water in the glass. First, you have to know the cross-sectional area. Okay, the area at the base of the glass times the height, If the cross-sectional area is circular, then you can calculate the area using pi r square. So the area for a circle is pi r square, where pi is 3.14, and the r is the radius. Radius is diameter divided by 2. So the volume that will be contained in this glass would be the area at the base times the height of the glass. Okay? So if this is the area and this is the height, you can calculate the volume. Okay? But if you pour this water, if you knock over the glass and the water is flowing, then you can calculate the flow rate by just using the cross-sectional area and the velocity at which the fluid is flowing. All right, so you have to try and get these little concepts, okay? Because using the hydraulic formula is very important in what we do in echo. Um, let's, so that's the right. All right. So again, when we talk about stroke volume is the volume that the ventricles pump out per beat. All right, so how can we calculate that volume using the hydraulic orifice formula? If you look at, let's look at the left ventricular flow track. If we use the left ventricular flow track, then we probably can calculate it. The left ventricular flow track, for all practical purposes, can be assumed to be circular. And as mentioned before, the cross-sectional area of a circle is pi r squared, whereas pi is 3.14 and r is the radius. So we can simplify that. Let's simplify that. So let's move on. So if we're talking about the left ventricular flow track, or even the right ventricular flow tract, these all flow tracts are circular, and the area of a circle is pi r squared. So pi looks something like this, and then r squared. So if you simplify that, pi is 3.14. The radius is equal, so you're going to multiply. Radius is the diameter divided by 2. And you have to square all of that. And that's squared. Okay? So you can further simplify that. So that's equal to 3.14. Okay, this is a 4. It's a kind of times. So that's d squared over 4. So 2 squared is 4. So it is 3.14 times d squared divided by 4. Now 3.14 divided by 4, so we're just simplifying the whole thing. 3.14 divided by 4 is 0.785, and that's times d squared. So that's when we simplify this. So when we simplify it, we get 0.785 times d squared. That is the area of the LVOT, and similarly the area of the RVOT. Left ventricular flow tract, because we're trying to calculate the volume of blood that's pumped out of the the left ventricle and the right ventricle per beat. So first, using the hydraulic formula, we know that the flow rate is equal to cross-sectional area times the velocity. So the area of any circular object or structure is 0.785 times d squared, where d is the diameter of the left ventricular flow tract or the right ventricular flow tract. And that is why when you're doing your echo, we routinely measure the diameter of the left ventricular flow tract for this purpose. So if you just plug in the diameter right here, you can calculate the cross-sectional area of the left ventricular flow tract. So all you need to do is to measure now the flow velocity, okay? The flow velocity. And that flow velocity is your VTI or TVI. So when you put your cursor across the left ventricular flow tract, you get an envelope, and this is done using the PW. Okay, so when you do this using the PW, you get an envelope. So that this velocity is actually your time, your velocity time integral. So you plug in your velocity time integral, and that will give you the stroke volume, which is equal to the cross-sectional area times the flow velocity. The flow velocity is your velocity time integral. Okay, so you have to try and get that concept, because this is something you're gonna use. All right. So the stroke volume, which is the volume of blood that's pumped out of, say, the left ventricle per beat, is equal to the cross-sectional area of the LVOT times the velocity time integral, or the time velocity integral. And the velocity or the time velocity integral is obtained by doing planimetry of the left ventricular flow tract envelope. And this is what it looks like. Okay. All right, so I showed you how to derive that. Of course, this is stroke volume, cross-sectional area times the time velocity integral. Then the cardiac output is equal to the stroke volume times the heart rate. So let me erase this. So if you wanna, so you're gonna use your Doppler to get your stroke volume. So on top you have your two-dimensional echo image. This is your 5-chamber view. Your cursor is right there. Sample volume is right at the left ventricular outflow tract. Okay, you don't want to be too close to the aortic valve. You need to be a little distance from the aortic valve, and you're going to get these envelopes. We did Doppler before, so you understand what these envelopes are. Your cursor is right here, and this is your LV cavity here. Blood is flowing from the LV cavity across the left ventricular flow tract, across the aortic valve into the ascending aorta. So the blood is flowing away from the transducer, so your flow is below the baseline, Okay, so this is your left ventricular flow tract flow, and it's done using PW, pulse wave Doppler. And once you do planimetry of the envelope, the computer will give you the velocity time integral, and you can see that it's just a length. Okay, it's just a length because you're integrating time and velocity. Okay, so you end up with just a length, because remember, velocity is the usual definition is meters per second, which is time. And you have time again, so the time cancels, so you end up just with a length or a distance. Okay, so stroke volume is equal to the cross-sectional area. So you have to calculate that cross-sectional area, which is 0.785 times d squared. And if you multiply it by the velocity time integral that you get from doing planimetry of this envelope, it's going to give you, it will give you the stroke volume. Again, the stroke volume is the volume of blood that is pumped out of the heart per beat. If you multiply the stroke volume by the heart rate, then you get the pulse volume. Okay? So, right. So that's an important concept you have to get, you know. All right. Okay. So this is what I showed you. If you're looking at the LVOT, it's circular. The area of a circle is pi r squared, whereas pi is 3.14. Radius is d over 2. If you square all of that, you get 3.14 times d squared over 4. 3.14 divided by 4 is 0.785 times d squared, where d is just the diameter of the LVOT. Remember, the diameter of the LVOT, parasternal long axis view, it's measured in systole just before the aortic valve, and you're going to measure from the tissue blood plane to the tissue blood plane, and that's your diameter. So you have to do these routine measurements. So this is doing it again. So the LVOT, the cross-sectional area is circular. Okay, pi r squared, r is the radius. Radius is d over 2. When you plug it in the equation, you simplify to that. Okay, so the stroke volume is equal to 0.785 times d squared times TVI. So whether you use the left ventricular flow tract or the right ventricular flow tract, the formula is the same for stroke volume. The diameter at the left ventricular flow tract and the right ventricular flow tract is going to be different. So you have to measure the diameter of the left ventricular flow tract and the diameter of the right ventricular flow tract. So cardiac output, which is the volume of blood pumped out of the ventricles per minute, is equal to the stroke volume times the heart rate. When we talk about the cardiac index, when you index anything, you divide it by the body surface area. So, and you will get normograms, you'll get charts that will give you the body surface area. We usually use the height and the weight, and there are normograms that will give you the body surface area. So you just divide the cardiac output by the body surface area, and you'll get the cardiac index. Again, when you index anything, you divide it by the body surface area. It's a much better way of giving the size of something or the value of something if you index that value. All right, so when we talk about pulmonary to systemic flow ratio, that we use that information if you have a shunt. And when we talk about a shunt, it's an abnormal communication, and that can occur at the atrial level, the ventricular level, or it can occur in the pulmonary circuit. Okay, so Shunts, we talk about atrial septal defect, ventricular septal defect, or patent ductus arteriosus. Okay, so when you have a shunt, as I said before, it's an abnormal communication between two structures. When you have an ASD, so it's an atrial septal defect, it's a defect in the septum, the atrial septum. So you will have blood flowing from the left atrium to the right atrium. When you have a ventricular septal defect, you'll have the same. Blood flowing from the left ventricle to the right ventricle. And then when you have a PDA, patent ductus arteriosus, blood is going to flow from the pulmonary, sorry, from the aorta into the pulmonary circuit. So in effect, what you're going to get an overload of blood flow into the pulmonary circuit. And that can be bad. Over a period of time, if that's not checked, it will be bad because it will result in elevated pulmonary pressures. Elevated pulmonary pressures, and if the pulmonary pressures are elevated sufficiently, then you'll have blood flowing in the opposite direction through these shunts. Instead of blood flowing from left to right, say you have a ASD, atrial septal defect, blood will normally flow from the left atrium into the right atrium. If it is left unchecked and it's a significant flow, and you develop pulmonary hypertension, elevated pulmonary pressures, and then you start getting backflow now from the right atrium across the defect into the left atrium, that can be bad. And that is what we call Eisenmenger complex. So that is why calculating what we call QPQS, which is shunt flow is very important. QPQS, shunt flow, is very important because if it is accurate, if you can accurately calculate this, it will tell you when to intervene, when to close the shunt. When the shunt is now too large, it's causing a problem. And we usually use 1.5 to 2. So if the QPQS, the shunt flow ratio, is 1.5 to 2, that's an indication to close the shunt. Okay? So all you do, so it sounds complicated, but it's a simple procedure. You calculate the stroke volume across the right ventricular flow tract, and you divide that by the stroke volume across the left ventricular flow tract. Remember what we said, okay? We said stroke volume is equal to point 0.785 times d squared, where d is the diameter squared. So if you're talking about QP, which is the flow across the right ventricular flow tract, you need to get the diameter of the right ventricular flow tract. You need to measure the diameter of the right ventricular flow tract. And then you're going to multiply that. So when you square the diameter, you multiply it by the VTI or TVI, whichever you're more comfortable with. Just give me 1 second, guys. Okay, so that's VTI, velocity time integral. So remember now, if we're doing the stroke volume on the right side, this VTI is, you get the flow across the pulmonic valve, and then that's the VTI. You just plane that envelope, and that will give you the VTI across the pulmonic valve. So to get the flow across the right ventricular flow tract, which is QP, the pulmonary flow, it is 0.785 times D squared, which is the diameter of the right ventricular flow tract, times the VTI, which is the velocity time integral across that envelope. Okay, and then to get the systemic flow, it's the same formula, 0.785 times D squared times the VTI, but your diameter now is the diameter across the left ventricular flow tract. And this VTI is the VTI of the LVOT, left ventricular flow tract. Okay, so you have to be comfortable. Just go over it. Okay, it's not that difficult, but you have to go over it. All right, so to get the pulmonary flow, again, the flow is the area times the VTI. So the area, we showed you this, is pi r squared. Pi is 3.14. R is d over 2. Square that to simplify to 0.785 times d squared. But when the diameter of the right ventricular flow tract, you have to get the short axis at the level of the aorta. Short axis at the level of the aorta. Remember, your pulmonary valve is right there. So your diameter is from one side of the wall of the pulmonary trunk to the next wall. That's your diameter. It's sometimes very difficult to get this diameter because it's not readily available, and it's more difficult to get than the LVOT diameter. So that is why this formula in a lot of cases is difficult to, it's not accurate because the diameter, the LVOT, the RVOT diameter is difficult to measure. But this is how it's done. Okay, so you're going to get the pulmonary flow, which is, as we say, is the cross-sectional area right here. And when we simplify that formula, it's 0.785 times d squared. So once you get this diameter, you square it. And to get the flow, the pulmonary flow, you multiply it by the VTI. And so let me erase this. It's too busy. All right, so you put your cursors right there. Your sample volume is across the pulmonary valve, and you get a flow which is moving from the right ventricular flow tract into the pulmonary trunk. It's away from the transducer, so it's below the baseline. And then once you plane the envelope, it will give you the velocity, the time velocity integral. And if you multiply that times 0.785 times d squared, then you get the pulmonary flow. You do the same thing on the left side, and it will give you so on the left side, stroke volume 0.785 times d squared of the left ventricular flow tract. So you get the diameter of the left ventricular flow tract, and then you get the LVOT TVI, and you'll get the systemic flow, and you put them. Okay, so you put your ratio of QP QS is this. So this would cancel, that would cancel. So all you need is the diameter of the right ventricular flow tract and your TVI, and your diameter of the left ventricular flow tract and the TVI. And that will give you the QP QS ratio. But remember that one of the limitation of this evaluation is measuring the diameter of the right ventricular flow tract. Okay, so that's very important to understand how to do it and to do it. Now, a very important equation in echo is the continuity equation. So it's actually a concept, and you have to understand the concept. So let's if you have a pipe, say you have a pipe, you have a long pipe, and at different points in the pipe you can assess the flow that's at the different points in that pipe. You have a pipe that's, say, 2 football field long, and say every few feet you can assess the flow. As long as there is no leak in the pipe, as long as there is no leak in the pipe, the flow at all the different points are going to be the same, unless the pipe is leaking. The flow at all points in the pipe is going to be the same unless you have a leak in the pipe. And that's basically what the continuity equation states. So if we use the heart as, say, a pipe, and there is no leak in the heart, okay, the heart is not leaking blood, then the flow across the pulmonary valve is going to equal to the flow across the aortic valve, is going to equal to the flow across the tricuspid valve, is going to equal to the flow across the pulmonary valve, because the heart is one continuous pump. And the flow across all these structures are going to be the same, even if you have a narrowing. So even if you have aortic stenosis, the flow across the aortic valve is going to be the same flow across the mitral valve, same flow across the tricuspid valve, same flow across the pulmonary valve, because the heart usually don't leak. You know, a leaking heart, someone who's dying because of trauma to the heart. So you don't need to calculate that. You need to resuscitate that patient. So you have to view the heart as a long pipe, and there is no leak in the system. The flow at any point in the heart is going to be the same. And that's based on the conservation of mass principle. And we use that knowledge to calculate stenosis and regurgitation. Okay? So this is the concept I'm trying to get across. So if this is a pipe, and say you have a narrowing here in the pipe, what I'm saying, the flow here is the same as the flow there. The velocity is going to be different. The area probably is different, but the flow is going to be the same. Okay? So, so remember we said that the flow is equal to the cross-sectional area times the VTI. So the flow at this point, if you could get the VTI, is going to be this. If you have a narrowing here, the area is going to be reduced, but the VTI is going to be large, because that flow, which is area times VTI, have to be the same. Okay? So the flow is the same. So that's the concept. If we know that the flow is equal to the area times the VTI at any point, and if we know the area at one point and the VTI at both points, then we can calculate the area of the area at the point that we don't know. And that is the principle we use to calculate valve area. This is a principle we use to calculate valve area. We use the continuity equation because the flow at all points in the heart is the same. And if we know the area at one point, the velocity, the time velocity integral at another point, and the time velocity integral at the area that we're trying to calculate, then we can calculate that area using the continuity equation. The flow here is the same as the flow at this narrowing. The flow at this point is the same as the flow at this narrowing. The flow is equal to the cross-sectional area times the velocity time integral. The flow here is equal to the area times the velocity time integral. Because the two are equal, then if the area here is smaller than the area there, then the velocity time integral have to be larger here so as to maintain equality. Okay, so that is the principle you use to calculate valve area. We're going to go over this when we do valvular heart disease, but you have to understand the concept. Okay, you have to understand the concept. You have to understand the concept because it's a very important one. Again, when we do valvular heart disease, we're going to go over these things, but you have to understand the concept. The last topic in hemodynamics is regurgitant volume. And as I say, we're going to introduce the concept here. And we're going to go over it again when we do valvular heart disease. So the important thing is to understand the concept, and then when we do valvular heart disease, you can fully appreciate what we're doing. So you have to have a visual picture of what we're talking about in order to understand this thoroughly. So when we have regurgitation, all right, so let's try and develop the concept. When we have regurgitation, let's take mitral regurgitation. When we have mitral regurgitation, what we're saying is that in systole, when the left ventricle contracts, we normally have all the blood flowing across the left ventricular flow tract, across the aortic valve, into the ascending aorta. But if you have mitral regurgitation, some amount of the blood is going to go backwards into the left atrium across the mitral valve. That is the definition for mitral regurgitation. So in systole, some of the blood is going to go forward across the left ventricular flow tract into the aorta, and some is going to go backwards. That's not a good situation because you want almost all the blood to be going forward because the body needs good blood flow. So if you have mitral regurgitation, some of the blood is going to go backwards into the left atrium. You can have different degree of mitral regurgitation. You can have mild, you can have moderate, and you can have severe mitral regurgitation. And that is dependent on the amount of blood that's going backwards from the left ventricle into the left atrium. So with mild mitral regurgitation, you have a small amount of blood going backwards. With moderate, you're going to have more blood going backward. And then severe, you're going to have torrential amount of blood, a huge amount of blood going backwards into the left atrium. So we can try and develop concept, and we can develop methods to assess the severity of this regurgitation. But first of all, you have to understand what's happening. So let's see if we can understand what's happening. So let's see if we can understand what's happening. So let's see if we can understand what's happening. So If we can calculate the volume of blood that's flowing across the mitral valve in diastole. Remember, the mitral valve normally opens in diastole, and then blood is going to flow from the left atrium into the left ventricle. Okay? So that is the flow of blood across the mitral valve, and that's, what's supposed to happen. But that flow of blood across the mitral valve is going to be mixing with what would normally flow plus the amount of blood that's regurgitating backwards into the left atrium. So remember what we said, if there is no leak in the system, you have a closed system, if there is no leak, then the flow across the different valves should be the same. But because you're having mitral regurgitation, blood is going backward into the left atrium, then the forward flow from the left atrium across the mitral valve into the left ventricle is going to be larger than what you would normally get. And it's going to be larger by the amount of regurgitating blood that's going backwards. So the flow across the mitral valve is going to be a bit larger than the flow across the other valves, assuming that the other valves are normal. Give me 1 second. All right, so the forward flow across the mitral valve is going to be mixed with the normal flow that would occur across the mitral valve plus the regurgitant volume that's going backwards into the left atrium. So if the other valves are normal, you can assume that the flow that would normally occur across a mitral valve would be the flow that is occurring across the aortic valve, the tricuspid valve, and the pulmonary valve, assuming that those valves are normal. So you can calculate the regurgitant volume if you take the flow across the mitral valve, which is now going to be mixed with the normal flow plus the regurgitant volume. So if you subtract from the flow across the mitral valve the flow, say, across the aortic valve, that difference is the regurgitant volume. So the concept is, and that is the same for any regurgitant valve. Because blood is going backwards into the left atrium, it's regurgitating back into the left atrium, the blood that's going to flow across the mitral valve when it opens is going to be much larger than normal. It's going to be the normal flow plus the regurgitant volume. So if you can calculate the flow that's going across the mitral valve, and you subtract the flow, say, across the aortic valve, which is normal, say it is normal, then the difference is the regurgitant volume. So that is one way of assessing the severity of the regurgitation. And it's a very important way of assessing the severity, because the more blood that's going backwards, the more regurgitation you're going to have. Okay, so what I just tell you is that the forward flow across a regurgitant valve is the sum of the systemic stroke volume, or the normal flow, and the regurgitant volume. So it's a sum of the normal flow plus the regurgitant volume once you have a regurgitant valve. If the forward flow across the regurgitant valve is QT and the normal flow is QS, Then the regurgitant volume is equal to QT minus QS, which is the forward flow across the regurgitant valve minus the systemic flow or systemic stroke volume. So this is the regurgitant volume. You need to understand the concept. Don't memorize the equation. The equation means nothing to you unless you understand the concept. And then the regurgitant fraction is equal to the regurgitant volume over the forward flow across the regurgitant valve. So regurgitant fraction. So in order to assess the severity of the regurgitation, you can look at regurgitant volume, that's the amount of blood going backward, or you can look at the fraction of blood that's going backwards, regurgitant fraction. So these are assessments. These are assessments of severity of regurgitation. The other method of looking at regurgitant volume is the so-called PISA method. I'm not going to do that just yet because it's you need to fully understand that. It's on, well, these are on almost all exams, so we're going to leave that for another time. But regurgitant volume, you can use just first principles and determine how significant it is, or you can use the PISA method, and we'll do the PISA method at another time.